talk today. John's been really active in the EPSCoR project in Focus 1, which is looking at microbial interactions of ecosystems. And I was really interested, I saw a paper in JGR last year that John's actually probably even better known, being a marine biogeochemist and an aquatic ecologist, I guess, or microbial ecologist, oceanographer. And he's done work from Hawaii all the way to the poles, looking at biogeochemistry issues and the impacts of climate change on marine systems. So now he's working on terrestrial systems in the Tenderfoot area, and so it'll be great to hear about that as well. So thanks, John. Thanks for coming.
Thanks, Kathy. Yeah, so today we're going to talk a bit about trace gases in soils, porous soils. Before going on to talk about why anyone would care to study that, must point out the sponsors. National Science Foundation funded virtually all of this work, either directly through their Hydrologic Sciences program or indirectly through Montana EPSCoR and the Montana Institute on Ecosystems. So thanks to all of them. We've also gotten a little bit of support from other parts of MSU, the Land Resources Department and the College of Ag and the DPR's office helped out. And some of our collaborators have also received some help from Department of Agriculture. So thanks to all those sponsors. And you can see I have this listed as myself et al., and that's because the et al. Would never fit on this slide. Let's see, go forward. These are just, this is not an exhaustive list of the people who have worked on this project. We have collaborators at a number of different institutions, mainly because our different projects have a lot of overlap, especially when it comes to the field research part. Data collection has been a lot easier by joining forces and using the same groups of people to collect different data sets. Won't go into all of these people here, but I would like to point out, let's see. Oh, yeah. So up here at the top, Ryan Jones in the microbiology department, who I understand is at a curriculum meeting. Very interesting. He's my co-PI in the current round of EPSCoR funding. And Eric Anderson is his grad student. Tim McDermott back there has been working on this with us for several years. And a whole host of other collaborators, students, conscripts, volunteers, children. I didn't get the dogs up here, but I did manage to get my kids and Tim's daughter up there. They've all helped out in the field or in the laboratory at one time or another. And a special thanks to the U.S. Forest Service for enabling us to do this work. Okay. A lot of different things we're doing up there at TCEF. I can only cover a little bit of it today, but just so you know the breadth of different types of research that are going on up there, or have been going on up there. Mainly today I'll just talk about soil gas fluxes and how they're influenced by microbial communities and a little bit about the landscape analysis of these trace gas fluxes. But I also want to point out how important students are in this whole project. Just a few, they pop up in these pictures all the time whenever you have, nobody ever sees me in the field, but they see these students. So this is Kathryn Gilliam. She's over, she just recently graduated from Montana Tech with her master's, and which was entirely on TCEF work and funded through IOE. We've got the dynamic duo from Duke over here. This is Kendra Kaiser and Aaron Seibold. They're PhD students at Brian McGlynn's at Duke University, and Kendra will be completing her PhD on this work. And then Keenan, who's in the back there. Keenan Brame up here, he was an undergrad working for us a couple years back. He the master of DNA extractions from soil. So thanks to Keenan for that. He's now a grad student. So, won't go into all these things, but back to trace gases. Well, which trace gases in particular? I'm actually only going to focus on two, methane and nitrous oxide. And like carbon dioxide here, those are greenhouse gases that can both be produced and consumed in soils. Responsible together for about 25% of the radiative forcing of total greenhouse gases in the atmosphere, so they are important to the global radiative balance. Like CO2, they're increasing over time. For reasons that will become more apparent as we go through this talk, we have not tended to focus as much on nitrous oxide, although you will see some data on that. We've really focused on methane, and most of the talk will be about methane. And one of the interesting things about methane is that if you look here, its increase over time has not been steady. This is the actual, down here is the actual annual growth rate. And you can see it, in fact, it completely stalled out here for several years in the 2000s. And if you were at Ben Poulter's talk last week, he basically admitted that we have no idea why that's happening, but things are accelerating again. And that, the reason we don't really have a clear idea of why that's happening in the methane cycle is because the global methane cycle is a balance between a whole lot of very large fluxes with big error bars on them. So you can see mostly sources from the terrestrial realm, both anthropogenic here in orange and natural, as in, for instance, wetlands emit a lot of methane in the green here. And those are balanced against basically one big sink, which is a chemical reaction in the atmosphere. And as you can see, there's big error bars on all these numbers, so it doesn't take much play in any one of these large fluxes to account for these changes in the accumulation rate in the atmosphere. Now, most of what I'm going to talk about has to do with this one green arrow here that's pointing the other direction. It's not a big flux, but this is the only natural sink of methane that isn't chemistry in the atmosphere. This is the oxidation of methane in soils by methanotrophic bacteria that live in the soils, and particularly in well-aerated forest soils. It may look like a small player in the overall budget, but if you consider the full range of estimates of the global soil sink, this error bar here, it's quite comparable to the actual growth rate of methane in the atmosphere, which has changed over these decades. So although a small player in the overall global budget, we really don't know how much this is influencing atmospheric methane. So we need to know more about what controls the soil sink. And I should point out, too, that it's known to be something that's sensitive to disturbance. I won't go into that in this talk, but it's something to consider. So our overall conceptual model for this study on methane on something like this, I mean, we look at the physical-chemical environment of the soil, and then we consider how that affects the local as in plot scale, methane source sink behavior, whether the soil is a source or sink, how strong that source or sink is. And that can be affected either directly through things like effects on transport of gas, or indirectly through changes to the soil microbial community. And this is actually quite a black box for which not a whole lot is known. Either way, whether it's directly, physically, or indirectly through the biology, the physical chemical environment affects the local sink source behavior. Then the idea is to try to integrate that here over space and time to come up with the methane sink for the whole forest, which ultimately feeds back into atmospheric methane and feeds back into changes in the environment. That's kind of the concept diagram, the one that goes on page 1 of the proposal. And so I tried to we had a lot of different hypotheses over the years, but I tried to just break it down to two main questions that we're trying to answer. And one is, does landscape position serve as a predictor of trace gas fluxes in these complex terrains? Can you tell something about what the gas fluxes should be based on where you are in the landscape? And secondly, is that predictive capability just something that stems from physics, from just the transport of gas through the soil? Or is there also some organized heterogeneity of microbial communities across the landscape? Neither one of these questions has been well answered to date. But it's important for scaling up to larger systems. So here's our study site, the Tenderfoot Creek Experimental Forest. It's up in the Little Belt Mountains in central Montana. If you've never been up there, it's a beautiful place. Lodgepole Pine Forest. You can see here's Tenderfoot Creek right here. Runs down into the Smith River eventually. And then all these subwatersheds around here are part of the experimental forest and feed into Tenderfoot Creek. Some of them, as you can see, have been experimented with by the Forest Service and all sorts of bizarre logging practices. But the one we're going to focus on today is absolutely pristine, and that's this watershed right here, the Upper Stringer Creek watershed, densely forested with lodgepole pine mainly, and with some narrow riparian corridors that look like this. Grasses, and it actually gets a little swampy when it's wet, and the stream running through here. Now, if you think about the question of scale, so this is just an elevation map here of this Upper Stringer Creek watershed. If you think about questions of scale, it's about 4 square kilometers. So on those really, really detailed, fine-scale regional models like Ben was talking about last week, this would be about 4 pixels in your model. If you're looking at a global model with 1 degree by 1 degree resolution, this is about a 2100th of that. So all the variability I'm going to show you in this entire talk could fit in 1/2100th of 1 pixel in a global model. So it's just something to bear in mind when you try to interpret these global budgets. And what we have here is a series of sites where we sample. In this case, we've got 41 separate sites, of which 32 we really heavily sampled, but there's 41 sites that we used in this study for sampling gases. And then there's a couple of MET stations here. This one up here has a 40-meter tower that sticks out of the canopy with eddy flux equipment on it. And then there's a smaller MET station down here in the riparian zone. Okay. Now, when people model methane flux, like in those global models, they basically model based on 2 things. One is reaction, and one is transport. So reaction here being the production of the gas minus the consumption of the gas, the net production of that gas. And that is typically modeled as a function of temperature, because these are microbial reactions, producing and consuming these gases. And also soil water content plays a huge role in this. I won't go into detail here, but this is just a schematic showing the relative biological activity of these different processes that produce and consume either nitrous oxide or methane or CO2 in the soil. And to look specifically at methane, we see that as soil gets saturated with water, because of the restriction of oxygen diffusivity into the soil, you can go anoxic and start to have methanogenesis, production of methane by methanogenic organisms. You also have denitrification going on, which affects N2O. I won't go into that too much, but the important thing is you only get methane production in the wettest soils. Whereas methane oxidation is something that you get where soils are well oxygenated. When you get really dry soils over here, you actually get some, in theory at least, get some inhibition of these processes just due to desiccation stress or lack of substrates. So the idea is, what do we expect methane flux to look like as a function of soil water content? Well, we expect that in very wettest soils we're going to get some efflux of methane to the atmosphere, but it will be diffusion limited. But over most of this forest, because most of the forest is dry, well-aerated soils, we expect a methane sink, and perhaps not quite so strong in the very driest soils. So that's what we expect. Now, the other thing you need is transport. In this case, transport is almost universally modeled just very simply according to Fick's first law, diffusion, which simply states that the flux is proportional to the concentration gradient of the gas. And this constant of proportionality is the diffusion coefficient. So basically, if the gas is going up as you go down into the soil, there's a flux out, and vice versa. Now, this is the only other equation I'm going to throw up here. I won't show you how this is derived, but one thing we've tried to take advantage of is the fact that you, in theory at least, should be able to calculate the flux of a second gas from the flux of a first gas if you know their concentration gradients. Because the diffusivities in free air, that's this D naught, are well-known functions of temperature and pressure. So that's essentially a constant. So in other words, if you go out in the forest and if you can make a measurement of this gradient in the soil for two gases, you can measure the flux of one of them, you can infer the flux of the other one. At least that's what we thought we would do, specifically by looking at carbon dioxide, which could be measured very readily in the field in a very short amount of time, and then trying to utilize what we could learn about carbon dioxide diffusion to help us calculate the fluxes of these other gases from their gradients, which are more easily measured. Again, that's what we wanted to do when we set out, but things aren't always so simple. But in practice, this is kind of what you do. You have these gas wells in the ground, and there's a schematic of them. So we're collecting air that's in the soil, 5 centimeters, 20 centimeters, and 50 centimeters. Gives us a gradient of the gas. At the same time, you can measure the efflux or influx of the gas using a flux chamber. In this case, this is our larger flux chamber. It's a Lycor 8100A. With all the bells and whistles. And it has an infrared gas analyzer in it, so you can get real-time measurements of the CO2 flux. And it's also set up so that you can pull physical samples out and bring them back to the lab and run them on the gas chromatograph and get a time course of the accumulation or disappearance of those gases in this chamber from which you can calculate a flux. So it's actually quite a bit of work to get a methane flux or a nitrous oxide flux because we don't have really portable sensors for those gases that can work at these low levels. So that's the idea. And what would actual data look like? Looks something like this, where here's the concentration data from gas wells. You can see CO2. This is just atmospheric here at the top. You can see at 5, 20, 50 centimeters, the gas concentration going up with depth. So that tells you there's CO2 coming out. It's respiration of both microbes and plant roots driving that. No surprise there. Methane, as we expected, is being taken up in these dry soils. So its concentration goes down with depth. N2O is a little weird. These are really small gradients, and they drive very small fluxes. That's one of the reasons why we focus so much on methane, because it's proved to be a much more tractable gas to study in this system. So this is exactly, this is the same site. So here are the concentrations we're measuring, and here's what's going on in that flux chamber. You see over time CO2 just being measured once a second. going up, and we actually use the initial linear part of the curve here to calculate the flux. Very nice decline in methane concentration, from which we can calculate the uptake of methane. The N2O, we can calculate a flux, but it wouldn't be significant. But we still try. So by doing this, at single sites, we're getting both the flux and the gradient of multiple gases at the same time. We should be able to come to some sort of agreement between them on what the diffusivity in the soil is. Unfortunately, well, I'll get to it in a sec, but unfortunately it doesn't really work out that way. We'll start with the most well-behaved one, which is methane. Surprisingly, these points here are calculated methane diffusion coefficients relative to methane's diffusion in free air. So these are all normalized to the diffusion coefficient in free air. Basically saying that if you had no water in the soil water content, you'd get about 25–30% of the flux that you would get in free air going through this soil. Makes perfect sense. We fit just a simple exponential model of soil moisture to this. These are the error bars. This is, in most cases, you will see soil gas diffusivities modeled as a function of air-filled pore space, which is just the porosity minus the soil water content. Right? I'm not going to go through the derivation, but I can show you that these are mathematically entirely equivalent if the porosity is constant. So that's why the curvature is exactly the same on these two curves. There's a few reasons why we prefer to use this approach, but they give you the same numbers. And this is for average porosity of about 60%, which we validated through direct measurements. Also, if there was a huge variability in the porosity across the landscape, that would be manifested in the variability of these measurements. In fact, we do get a pretty good correlation here. I think the R-squared is about 0.7, shows that porosity can't vary that much across the landscape. So we have pretty good confidence in these numbers. And what gives us even more confidence?
Can you explain what the dots are? So those are your samples that you take every year?
No, these are times when we have deployed this chamber and done these time courses. So that's why there's not as many of them as the full data set. So these are diffusion coefficients calculated from measuring both the gradient and the flux of the gas at the same time at a point on the landscape. And so these include many different sites over a period of about 2 years. It's just a lot of work to do. That's why there aren't that many data points. The idea here was we do this more difficult stuff on a more limited basis and use that information to enable us to take much more facile measurements of that gas gradient and turn it into fluxes.
Good job. Can you get back to your methane profile?
Mm-hmm.
Why does it increase towards the surface? Is that because there's methane production or the methane oxidation below the surface? I guess
it's the oxidation below. So if you have a decreasing gradient with depth, you have the flux down.
Right, but why is methane oxidation only occurring then in the lower depth? Why do we get no methane oxidation at the surface?
That's a good question.
Okay.
I'll come back to that.
All right, yeah, fine.
Yeah.
Just start puzzling me.
No, I will come back to that. It's very important for this, actually.
Okay.
Some of you who looked at diffusion of gases in soil, I don't know how many of you have done that, but if you have, you're probably used to seeing diffusion in soils not modeled as an exponential function of soil moisture or air-filled pore space, but as a power function. I actually prefer the exponential, but just to convince you that this works, these are 3 different models. We're on a log scale now, so exponential looks like a straight line. This is diffusion coefficient of methane versus soil moisture. Here's that same curve I showed you, only now it's linearized. And these are 3 other power law models that are popular in the literature. I think one's Buckingham and a couple of different Muldrup formulations. You can see that until you get to the very, very, very waterlogged soils, they'll agree reasonably well. So it really doesn't matter which one you use, is what I'm trying to get at, but we've been using this exponential. And just so you know, these yellow points are the ones where the methane's coming out, net efflux, whereas the black ones are methane's going in. So there doesn't seem to be any sort of isotropic thing going on here. You get the same diffusion coefficient whether gas is going out or going down, which is nice. Okay, but then remember we wanted to use CO2, and this is our other flux chamber for CO2. This is actually very small and portable. So this is one you give to the grad students and have them run all around the forest, hitting as many sites as they can all day long, every week for 2 years. And every one of these little black points is a measurement of CO2 flux from this chamber. It's actually an average of 3 measurements of CO2 flux from this chamber. So that's a whole lot of measurements that were made. And we wanted to be able to use those to inform our diffusivity calculations. But we had to validate it with that other glycol chamber, which are the red dots here. Much smaller data set, but overall, the CO2 kind of goes up with soil moisture, as you might expect. And the two seem to agree reasonably well, but not being, that wasn't enough. I mean, there's a paper by Mills et al. Where they directly compare these instruments. No difference. We've done some direct comparisons of these instruments. As long as they're properly calibrated, they give the same result. So we're confident in the CO2 flux measurements. So now if we do the same thing with CO2 that we just did with methane, when we try to get the diffusion coefficient empirically from gradient and flux, we come up with something like this. And again, this is on the log scale, so the exponential fit is a straight line. And you can see that the Lycor, results are a little lower than the EGM4, and that's probably because most of these data were collected by me, and I wasn't really out there at the height of the growing season. That was more early season and late season. But they show the same general pattern, the same general decline with soil moisture, which is good. But then there's a real problem with this, and that is this. What I've shown here on this dotted line is the theoretical maximum diffusivity that you should be getting, about 40%, in a perfectly ordered soil that's perfectly dry. So this is like, glass spheres, perfectly dry, packed. That's as much diffusion as you should be getting out of there. And you see that we're getting, in many cases, a whole lot more than that. Something is wrong here. And in fact, what makes it even worse is that even at these very high soil moistures, where there should be a real significant depression of the diffusion, you're still getting these high diffusion coefficients. Can't be right. So what's going on here? Here, I just got them all in the same plot. So this, I didn't label it here, but the black is the methane data I already showed you. The red is the CO2, and the blue is the nitrous oxide, for what it's worth. So both for CO2 and nitrous oxide, you have these unreasonably high diffusion coefficients empirically determined, using exactly the same equipment at exactly the same time as with methane. So why does methane work so much better than CO2 or nitrous oxide? And this is where Skid's question comes back in. But what we think is happening here is we're trying to measure diffusion between 5 centimeter depth, which is about the shallowest that we could possibly measure using our equipment, and the atmosphere above. But that's assuming that you have constant production rate through that layer from 5 up to the surface. If what you really have, as in the case of CO2, it's a very narrow, very thin layer near the surface, this humus of high CO2 production. It throws your old calculation off. Fick's law no longer works because you can't actually measure this gradient accurately. The gradient, the real gradient that's driving that flux, is a lot higher than what you're measuring. And unless you had really, really tiny CO2 probes that could fit right in there, you wouldn't be able to tell this. And this is thought to happen particularly when the surface soil is wet, especially when it gets wetted after a period of dryness. Microbes take off, start respiring. On the other hand, methane, you actually have a zone of very little methane consumption in that upper 5 centimeters. At least that's how we've modeled it here. It's very little affected by, I should say, the consumption rate. The methanotrophy that's going on is very little affected by water in this surface layer. And this has been seen in a lot of forest soils, especially pine forest soils. And it's thought to be related to inhibition of the microbes by compounds that are being leaked out by the trees and from their needles, pinene, various monoterpenes, actually inhibiting the methanotrophic activity. And that actually, this is my hokey little model, but here's some real data from Ralph Conrad. I'm sure you believe him. This is from 1993, where they looked at the same thing in a pine soil. And here you can see very, very high respiration CO2 production in that upper centimeter. We're just not able to take that into account with our scheme. And you can see there's this zone in the upper few centimeters of very low methane uptake. Most of that methane oxidation is going on below 5 centimeters. But this is consistent with what we're seeing, and it really means that we have to just go with the empirically determined diffusion coefficients for methane that we have. We're not going to be able to use ones from CO2 and transfer them to other gases. It's not going to work. So what happens when we do that? Okay, now we finally got it. We finally have a way to measure methane flux out of the soil, or out of, or into the soil at a whole lot of different places over a whole lot of times. This is just this is from Kendra Kaiser's work. Just looking at the 2013 season. If you remember the conceptual diagram I showed earlier of how methane flux should vary with soil water content, it looks something like that. In the very wettest soils, you have actual emission of methane, and then these are all these blue ones are the in that riparian corridor. They're the only soils that ever end up putting out a significant amount of methane. And then all these hill slope positions, you have methane, net methane consumption that seems to be stronger in drier soils, which makes sense from the point of view of methane needing to diffuse into the soil to be consumed. So that's pretty gratifying. Looks about right. I won't go much into this, but this is just to show you that we did collect a whole lot of data on CO2 and nitrous oxide as well. But so this is CO2 in the top, methane, nitrous oxide. These are all 2 seasons combined now, 2012 and 2013 seasons combined. These are fluxes as a function of either soil water content on the left or soil temperature on the right. Some of them just are shotgun blasts, but I'm going to focus on is these ones from methane and try to convince you that there really is some organization to how these are distributed. One thing that's kind of neat here, I just noticed that both the efflux and the influx seem to be maximum right about the mean temperature of the soil at the site. So maybe the microbes are adjusted to this temperature. Won't go any more into the actual raw data, but let's start to look at patterns across the landscape. What we have up here is just water. So this is snow melt early in the season, and then later on we have these precipitation events. So most of the snow melt occurs right around here. If we look at a riparian site, this is the groundwater level here on the blue line here, going down. It never really dries out. At a toe slope site, it dries out, but it takes a while. And then up on the hill slope, it dries out, soon after snow melt. And you can see that where this groundwater level finally gets low enough for us to actually have our wells be not flooded, we start to measure methane efflux. And then in these upland sites, you get strengthening methane uptake as things dry down. So how can we utilize this information? Well, one thing is to look cumulatively across the whole season. So this is cumulative methane flux versus time across the season. So we start at 0, and then we keep sucking up more and more methane, or producing more and more methane. Basically what you find is that the riparian sites are always about neutral to sources of methane over the whole season. The hill slope sites are always net sinks. But there's quite a lot of variability between different sites across that whole season. I don't know, a factor of 6 or 7 there, it looks like. The question is, do we know anything about what's driving the differences in these upland sites in terms of their sink strength?
John, each one of lines different locations?
Yep, everyone's a different site over the entire 2013 season. So they're all taking up methane, but to different extents, and why? So to see if landscape position has something to do with it, what Kendra did here is run a multivariate analysis to try to see if any of these factors influenced the whether it influenced the methane flux, and whether we could use these factors to model the methane flux. And these are just terrain descriptors like slope and aspect, and elevation above the creek, and distance from the creek, and gradient to the creek, and upslope accumulated area, topographic water index, all things having to do with the landscape itself. They're not all independent. But what was gratifying is that when she ran the model, we came up with an R squared of 0.47, almost half of the variability explained by just these 4 variables. And they were highly independent of each other, which is also gratifying. And these are slope, aspect, distance from the creek, and upslope accumulated area. These are all things that can be readily calculated from our digital elevation model of the digital elevation map of the site. So she did that, and then plotted for each one of those sites the cumulative flux over the season that we measured versus what the model would spit out. Got this nice relation here, and that's the 0.47 R squared. So if you take this relationship and apply it to all the pixels in the watershed, you get something like this. This is what we've been trying to get at, is what does the overall cumulative seasonal uptake of methane look like across this complex watershed. And you can see it is quite complex. I mean, we have big areas of rather strong methane uptake, and then these convergent areas where it's a weaker uptake. And then down in the riparian zone, it's actually net methane emission. Now, because the riparian zone is such a small part of the total area, the overall result is that this is a sink for methane. But now we can start to look at some details. Why different parts of the landscape may have different fluxes over the year. And just quickly, since James and Paul are here, we did some eddy covariance work too to try to look at the top-down approach. So we have high-frequency methane analyzers. We deployed them both on the 40-meter tower and then down here on the short riparian tower to use the eddy covariance technique to try to see if we could constrain the overall methane fluxes, both in the whole forest and down in this riparian corridor, and see whether it whether it matched with our boots on the ground approach. At first it looked pretty good. The riparian sites were net emitters. The tower site showing the whole forest as a net sink. But these are really small numbers that cluster right around the axis. Another way to look at them is in terms of a single day. So this is like midnight to midnight, all the data collapse onto it. And you can see that where we get the big values is all in the daytime. And I think that's largely artifactual. These dots in the middle are our actual measurements on the ground. Basically, the signal we're trying to look for is too small to be resolved with this technique. The thing I should point out is all these dots here out in the middle of the night, we didn't actually make anyone sit up all night doing methane flux measurements. I actually took one of those open path analyzers, turned it into a closed path analyzer, and plumbed it into the flux chamber so that I could set it up and let it run, taking measurements every hour for 24 hours to get diel measurements. This is what the diel measurements look like. It's two methane absorbing sites, no diel signal whatsoever. So that also gives you an idea that what appears to be a diel signal in the eddy covariance data is probably not real. There does seem to be a little bit of a diel signal in the methane efflux in the riparian zone. It's not much. So anyway, this is just something from another paper looking at a similar system. And they got similar results, and they did some error analysis and showed that you just can't say that these fluxes are significantly different from zero. And one of the reasons for that is what I've got here is there's a lot of these, Paul scans this much better than I, but there's a lot of these corrections that go into the eddy covariance data before you get a final flux out of it. And what I plotted here is the uncorrected data in blue, and then the final fluxes in orange. What you can see is that the signal we're looking for is small compared to the magnitude of the corrections we have to apply to get that signal. It leaves me very much in doubt whether we can actually measure fluxes this way at these very, very low levels. So the last section here I want to go over is about 10 minutes here. So back to microbes. The microbes involved in methane cycling vary over the landscape in predictable ways. This is a paper that just got accepted and applied in environmental microbiology. This was from 2012. We went out and measured 9 different sites, all in one day. So this is one day's data, 9 different sites, published papers, so that's not so bad. And we showed indeed that there are differences across the landscape. This is a principal coordinate analysis. You can see that these dry upland sites cluster out very far from the wet riparian sites, and then the transitional sites are somewhere in between. We think that at least that principal component 1 there is probably largely a function of soil moisture, or at least it's showing some sort of dichotomy between the dry sites and the very wet sites. Here we have phylogenetic diversity plotted against soil water content. You can see again that the riparian sites are more diverse than the upland sites. And then if we look specifically at organisms that are involved in methane cycling, the methanogens, which produce methane, the methanotrophs that eat it, we again see some very distinct patterns across the landscape. We only find methanogens right in the riparian zone, right next to the stream. Don't find any of them up on the hill slopes. And where they are at, where they're producing methane, that's where you find the largest amounts of methanotrophs, because they're eating all that methane that the methanogens are producing. And they're mostly this type 1 methanotroph, which likes high methane concentration, can take up a lot of methane. Whereas if you go up on the hill slope, much, much lower numbers of methane oxidizers, and they're primarily this type 2, which are very good at taking up methane at very low concentrations, so atmospheric methane. So you can see this dichotomy between riparian and upland, not only in the total microbial community, but also in specific groups of microbes that are involved in methane cycling. So those 9 points in one day, that wasn't enough, so we went out the next year and did a massive sampling, 7 time points, 32 sites, 2 or 3 depths per site, 495 total DNA samples, about 16 million sequences. And that's what Ryan's working on right now, analyzing all that data. So we'll get a better idea of whether these patterns hold up over time and over space. And we did from this, just that small number of sites on one day. This is actually some of Ryan's data. He just gave me this yesterday. And this is all sites, all times from 2013. And once again, you see this strong dichotomy between riparian and upland sites. But within riparian and within upland, there's also quite a lot of variability. And the challenge is to figure out what's driving that.
John, do you know what the symbol colors?
Yeah, this is the, these are the riparian ones. And the blue and red are, the red I think is the high upland, and then the blue is the lower upland, so just above the creek. And I think these points here are just maybe ones where we misidentified the site as upland when it should have been riparian, because these are, that definition was based on 2-meter elevation above the creek. And in some cases, you can have riparian sites that extend higher than that and vice versa. In fact, Ryan and I were talking about how this, using these microbial community structures might actually be a more effective way of separating riparian from upland for other studies than using elevation alone.
There was that one site, John, that we referred to, it generated a lot of discussion in preparation for that manuscript, that transitional site.
Yeah.
Any chance that those blue dots towards riparian might represent that?
Could be. I don't know. We didn't have time to actually go in and look at which ones were which. He just plotted this yesterday. But it's interesting. And another thing he's doing is starting to look at how the community changes over time. So this is just one single site up on the hill slope. And this is the soil water. You can see that, after snow melt, dries, and then it's dry out here into September. And this is what the microbial community is doing. It's sitting over here and it's moving around a little bit, not doing a heck of a lot until late in the season when things really dry out. All of a sudden, wham, 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 completely changes. What's driving that? That's something we have to better understand and start looking at all of these sites rather than just one. Another thing we're doing is we're starting to look at uptake kinetics, methane uptake kinetics, to see if those vary in the same ways that the microbial communities do. And so far it looks pretty good. This is some work we did in 2014. These 2 sites that appear to have quite different kinetics from these 2 sites. These ones on the top are just above the riparian zone, and these ones down here are way, way up high on the hill, very dry. So both the KMs and the Bmaxs for these were quite different. We need to build up a larger data set on these. But the idea there is that, if microbial communities are different, then perhaps their intrinsic enzymatic kinetics are different too. Last slide I'll show here is something that we've been working on that Eric and Ryan and I did this summer. We started to think, well, we've got this amazingly massive amount of data on the microbial communities in this one little watershed. Do these same patterns hold up in the next watershed over, or the next mountain range over, or 2 or 3 mountain ranges over? So we went out and we sampled 4 riparian and 4 upland sites in each watershed at 5 and 20 centimeters, and those DNA samples have been extracted and sent out for sequencing. We also measured soil temperature, water content, and CO2 efflux. And we did that in 10 different watersheds this summer, 5 right there in TSEF, they're right next to each other, 2 over in Lubrecht, and then 1 each in the Gallatin and the Big Belt here, and then up in the Flathead. So I'm really looking forward to seeing that data. I think it would be really interesting. I mean, maybe the patterns will all be exactly the same. I don't. That'll tell you something too, but maybe they'll be different. Just don't know. I don't think anyone's actually tried that before. Conclusions then. So nearly half of the variability that we've seen in soil methane fluxes in this watershed can be explained by landscape position alone, which makes for some tractable scale-up. Secondly, the soil microbial communities and their activities also seem to display some organized heterogeneity, and that may be related to seasonal patterns of water redistribution around the landscape. And that's all I have. Thank you.
John, that's time for questions.
I did. Oh. Paul.
One, if you go back to that first equation,
The what now?
right near the beginning.
Oh, just fixed thought? Yeah.
I mean, it doesn't solve the mass balance, it powers the same dynamic each layer like you talked about here.
Right. The idea is there are practical limitations to how fine a scale you can measure those gradients at.
No, but I'm saying is between the measurements where you see that source that are distinct from all the compounds, so you have to add equations.
That's if you're doing a reaction diffusion equation, like 6-second law.
There are reactions. I mean, if you're using sulfur hexafluoride, right, that's not going to react with anything.
Right. Yeah, I mean, no, it's true. That's why you want to measure that gradient as close to the surface as possible to minimize the effect of that.
So this, I guess, brings up my second point, especially close to the surface. I mean, diffusion is not really what's happening. It's a lot of diffraction. And Bill Madsen, for example, has shown that analytically, approach that people are starting to use this kind of enhanced diffusion. You're basically using a lot of that.
Yeah. We chose not to do that, but one thing I will say about that is that if advection were playing a big role, it should be doing so for, should be affecting all the gases. And we really get excellent results for methane based on diffusion alone. I really don't think advection is playing a big role in this, but your point about the actually being production in the shallow layers, absolutely well taken.
One thing is that the diffusion assumption increases as you get down into the soil, but doesn't actually there, especially in the top layer.
Yeah,
Diffusion happens, but it's probably harder to actually.
Oh yeah, I mean when you're in the dust layer, you're not even getting vertical diffusion anymore. You're getting gas going in all different directions from those crumbs of the
diffusion. Well, my argument would be that would be, you always have diffusion, but it's actually.
Well, not in a closed chamber.
Yeah, because you're changing.
No, it's actually pressure compensating.
Any air movement, I mean, it's like.
There's no air movement in that chamber. It may be in the real world outside of the chamber.
No,
absolutely.
Because there's changes in temperature between the walls of the chamber. There's always going to be air movement like that.
Yeah, well, we could argue all day about the pros and cons of flux chamber measurements, but you got to go start somewhere to make these estimates. Now, if you guys could get the eddy flux stuff to be more sensitive, then we could just do that.
Their point about that, I mean, there really is no such thing as unconnected flux because infections are getting the mass out or surface atmospheric being. So yeah, I mean, the fluxes are just really small.
They're really small.
That open path.
Eddy Pro does spit out an uncorrected flux. So I'm assuming that folks at Lycor know what they're talking about.
Exactly, something we can. A closed path system might be necessary. Open path is a cool idea.
Yeah.
That's really
The thing is, we spent $88,000 on 2 open path sensors, so.
yeah. The optical length of that thing is what it is. So
Yeah, it's 30, yeah, it's about 30 meters.
It solves one problem I'll always using it not having to have that.
and again, we could have a whole session on the pros and cons of heavy flux measurements.
Can I ask a boneheaded question, following up on Paul's very detailed? So the F-score grants Montana's vulnerability to climate change. So connect the dots so I can understand what you're finding that's going to help us understand that.
Well, that will be for focus 3, right? We're focus 1. No, that's a joke. I mean, the idea is that in the case of something like methane, if you look to what global modelers are doing, they're basically modeling the uptake of methane in the soil solely on the basis of 2 things, temperature and soil moisture. And those are moving targets in terms of changing climate. So if we can help them to better model that, then maybe they can use that to make their predictive models more accurate. But we ourselves are not that adept with modeling it.
With your landscape scale, we're across the drainage of TSAP in 13, and then last summer all over hell and back.
Yeah.
If you can start modeling across landscapes, then all of a sudden those projections become much more defined.
Yeah, that's what we're hoping. I mean, it's.
Yeah,
Could you go to that slide about the moisture? You made a comment about.
Which one?
Keep going. Right, flip back up, I think. Yeah, over in the middle right, isn't that the moisture of methane?
That's temperature.
Oh, temperature. Yeah.
Yeah.
So,
yeah, the average temperature is about 11 degrees up there.
So if the soil temperature were to shift on average across the year by a degree, or 2 degrees, that kind of data might be helpful in terms of some interpretation there.
Yeah.
I don't want to get in a hand with it.
No, I don't either, but
You brought that, you pointed that out, John. I thought, well, yeah, that's an interesting way of looking at it.
Yeah. In fact, I just saw this one for the first time on Monday. So I'm hoping that Kendra follows up on that in her dissertation.
Sure. Based on that, though, John, maybe as well, isn't one of the real factors with climate change, based on that data, the drying phase from that soil water content, if you're going to much drier conditions, right, you drive a lot of the soil from 30% down to 20%, right, so then you can actually get a significant change in your...
Yeah, if you want to go out and drain wetlands, I mean, that's a way to solve the methane problem. No, but people are doing exactly the opposite. They're building riparian areas.
Right.
In order to solve other problems like nitrate runoff. But
sometimes that's another thing that with changing climate and changing temperature regime, that looks like there's a fairly relatively narrow range. You go from one regime to another that's then could be quite tractable.
Indeed. In fact, when we were trying to sell some of this work to the NSF Ecosystems program, Tim, you may remember this. One of the reviewers actually was surprised that we were getting any methane emissions in this forest. Couldn't believe it. It's a dry upland forest. There shouldn't be any methane coming out of there. There it is.
Huh. Well, great. Well, thanks, John. This is good.
Thank you.
Really enjoyed hearing about it.